Welcome to today's class. Today we are going to discuss about the last topic in this module, that is stability factor. So we have already discussed what is the need for bias stabilization. We already know that the transistor parameters are highly temperature dependent. That is, the parameters like beta for a transistor changes from one unit to the another. So we need bias stabilization for fixing the Q point. So bias stabilization is the process of making the operating point independent of temperature, parameter variations, and transistor replacement is called as bias stabilization. So we have already discussed the temperature dependence of the collector current IC. We know that the collector current IC will be increasing drastically if the reverse saturation current ICBO increases. That is, for every 10-degree rise in temperature, the reverse saturation current ICBO will be doubling. So because of that, our IC will be increasing. As a result, power dissipation also will be increasing. So as the power dissipation at the junction is increasing, the temperature again will be rising. So this process will be repeating, and finally it will be coming to a situation like thermal runaway. So the main point is here that when the reverse saturation current is increasing due to the rise in temperature, the IC getting changed. So as the IC is getting changed, our Q point will not be stabilized. So this temperature dependence of IC have to be reduced. And also, the major requirements for a biasing circuit is that to fix operating point in the middle of active region so that the transistor will be working as a linear amplifier. And also we have to stabilize the collector current against the variations of temperature. Also we have to make the Q point independent of transistor parameters like beta, that is current amplification factor. So if a transistor is replaced, the beta will be changing. So because of that change in beta, the operating point should not affect. So these are the requirements of biasing circuit. Okay, so coming to the stability factor, there are three types of stability factor. First one is the stability factor S. Stability factor S is the change of collector current with respect to the reverse saturation current, keeping beta and VBE constant. So the stability factor S is defined as the change happening in the collector current with respect to reverse saturation current ICO, keeping beta and VBE constant. Beta means current amplification factor and VBE means base emitter voltage. Okay, so it can express like this: S is equal to dou IC divided by dou ICO, which is equal to delta IC divided by delta ICO, where ICO is the reverse saturation current. ICO is the reverse saturation current. Also it can be expressed like delta IC divided by delta ICO. Okay, so this is the stability factor S. So here change in collector current with respect to reverse saturation current, keeping current amplification factor beta and base emitter voltage constant. Okay, now coming to the stability factor S dash, it is the variation of collector current with respect to VB. Previously, stability factor S is the variation of collector current with respect to reverse saturation current. So the stability factor S dash is defined as variation of collector current with respect to VBE. VBE means base emitter voltage, keeping beta and the reverse saturation current constant. So S dash can be expressed like delta IC by delta VBE or dou IC divided by dou VBE. Okay, so where VB is the base emitter voltage. So this is the stability factor S dash. And third stability factor, that is S double dash, is the variation of collector current with respect to beta, keeping VBE and reverse saturation current constant. So S double dash can be expressed as dou IC divided by dou beta or equal to delta IC divided by delta beta. Okay, so this is the change in collector current with respect to change in current amplification factor. Okay, where beta is the current amplification factor. So overall IC we can represent like this. Delta IC will be equal to stability factor S into delta ICO plus stability factor S dash into delta VBE plus stability factor S double dash into delta beta. So this is all about stability factor. Okay, so this is a fixed bias circuit. Okay, here base resistance and collector resistance is connected to VCC. Okay, so for finding stability factor of a fixed bias circuit, we all know IC can be expressed like beta IB plus beta plus 1 ICO, where ICO is the reverse saturation current. Okay, normally we used to write IC equal to beta IB, and we are not writing these terms beta plus 1 into ICO because we are neglecting this term, as this will be ICO is a very small current, so we used to neglect this ICO term. So IC can be expressed like beta IB plus beta plus 1 into ICO. And also from the input analysis of fixed bias circuit, we will be getting IB is equal to VCC minus VBE divided by RB. Because in input side, if you are taking KVL, we can write VCC minus IBRB minus VBE equal to 0. From that we will be getting IB, which will be equal to VCC minus VBE divided by RB. So putting this, if you are putting this IB in this equation, we will be getting like IC is equal to beta into VCC minus VBE divided by RB plus beta plus 1 into ICU. Okay, so differentiating both sides with respect to IC, we will be getting what? If you are differentiating both sides with respect to IC, what we will be getting? Dou IC divided by dou IC, which will be equal to dou by dou IC of beta into VCC minus VBE by RB plus beta plus 1 into dou ICO by dou ICO by dou IC, dou ICO by dou IC. So from here we will be knowing this term is a constant term, so this will become 0. Here dou ICO divided by dou IC, how we can write? We know that stability factor S is equal to dou IC by dou ICO. So dou ICO by dou IC will become 1 by S. So if you are substituting that here, we will be getting LHS will be equal to 1, which is equal to, here this is a constant term, so we can write it as 0 plus beta plus 1 into dou ICO by dou IC, how we can write? Which is equal to 1 by S. So this will be becoming S is equal to beta plus 1. S is equal to beta plus 1. Like this we will be getting. Okay. So that is what, if you are differentiating, we will be getting 1 equal to, this is the LHS side, dou IC by dou IC, 1 equal to, this is a constant term, so it will become 0 plus, here beta plus 1 into dou ICO divided by dou IC, how we can write? 1 by S. So finally we will be getting S is equal to beta plus 1. So here you can see the stability factor is dependent on current amplification factor beta. So if the transistor is replaced here, the stability factor will be changing. So as the stability factor will be changing, the Q point will be shifting. So in the case of fixed bias circuit, if the transistor is replaced, the stability factor will be changing. So as a result, the Q point will be also shifting. So because of that, we are saying that the fixed bias circuit is the least stable circuit. Okay, now coming to the stability factor for collector to base bias circuit. This is a collector to base bias circuit. Here you know that a base resistance is connected to the collector side. So this base resistor will act as a feedback from collector to base. Okay. So for a collector bias circuit, stability factor will be equal to beta plus 1 divided by 1 plus beta into RC divided by RC plus RB. So ഇവിടെയും നമുക്ക് ഈ സ്റ്റെബിലിറ്റി ഫാക്ടർ കിട്ടാൻ വേണ്ടി നമ്മൾ സെയിം സ്റ്റെപ്പ് തന്നെയാണ്, നേരത്തെ കണ്ട സെയിം സ്റ്റെപ്പ് തന്നെയാണ് യൂസ് ചെയ്യുന്നത്. അതായത് ആദ്യം IC which will be equal to beta into IB plus beta plus 1 into ICO എന്നറിയാം. ഓൾസോ കളക്ടർ ബയസ് സർക്യൂട്ടിൽ ഇൻപുട്ട് അനാലിസിസ് നടത്തി കഴിഞ്ഞാൽ we will be getting IB which will be equal to VCC minus VBE minus ICRC divided by RC plus RB. This we have already derived when we studied collector bias circuit. So ഈ ഒരു ഇക്വേഷൻ എവിടെ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് കൊടുക്കുക, ഈ IB ക്ക് പകരം സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് കൊടുക്കുക. Then differentiating both sides LHS and RHS with respect to IC ചെയ്ത് കഴിഞ്ഞാൽ we will be getting stability factor like S is equal to beta plus 1 divided by 1 plus beta into RC divided by RC plus RB. വളരെ സിമ്പിൾ ആയിട്ട് ഇത് നമുക്ക് കിട്ടും. ഇപ്പം ടേം ഇതിനെ നമ്മൾ ഡിഫറൻഷിയേറ്റ് ചെയ്യുകയാണെങ്കിൽ, സോ ഇത് എങ്ങനെ കിട്ടുന്നതെന്ന് വെച്ചാൽ ഇവിടെ ഈ IB നമ്മൾ ഇവിടെ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് കൊടുക്കുക. IB സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് കൊടുത്തിട്ട് നമ്മൾ ഈ ഒരു ഇക്വേഷനെ നമ്മൾ ഡിഫറൻഷിയേറ്റ് വിത്ത് റെസ്പെക്ട് ടു IC വെച്ചിട്ട് LHS ഉം RHS ഉം കൂടി നമ്മൾ ഡിഫറൻഷിയേറ്റ് ചെയ്ത് കഴിഞ്ഞാൽ we will be getting 1 is equal to, okay, ഇവിടെ VCC minus VB divided by RC plus RB എന്നുള്ള ടേം കോൺസ്റ്റന്റ് ആയിരിക്കും. സോ ബീറ്റ ഇൻറ്റു VCC minus VB divided by RC plus RB എന്നുള്ള ടേം 0 ആവും ഡിഫറൻഷിയേറ്റ് ചെയ്യുമ്പോൾ. നമുക്ക് ആകെ ബാക്കി ഉണ്ടാവും എന്താ, ICRC ബീറ്റ ഇൻറ്റു മൈനസ് ബീറ്റ ഇൻറ്റു ICRC. അപ്പൊ എന്താ, മൈനസ് ബീറ്റ ഇൻറ്റു RC, ഓക്കെ, RC. ഇവിടെ എന്താ, ഡോ IC ബൈ ഡോ IC. ഇവിടെ ഡിനോമിനേറ്റർ സൈഡിൽ RC പ്ലസ് RB അല്ലേ, RC പ്ലസ് RB. ദെൻ ഇവിടെ വന്നിട്ട് പ്ലസ് ബീറ്റ പ്ലസ് 1 ഇൻറ്റു ഡോ ICO ഡിവൈഡ് ബൈ ഡോ IC. ഡോ ICO ഡിവൈഡ് ബൈ ഡോ IC നെ നമുക്ക് എങ്ങനെ എഴുതാം, 1/s എന്ന് എഴുതാൻ പറ്റില്ലേ, 1/s എന്ന് ഈ ഒരു ടേമിന് എഴുതാം. സോ ഇത് ലെഫ്റ്റ് ഹാൻഡ് സൈഡിൽ എടുത്തു കഴിഞ്ഞിട്ട് സിംപ്ലിഫൈ ചെയ്യുന്ന സമയത്ത് നമുക്ക് ഇങ്ങനെ കിട്ടും, S is equal to beta plus 1 divided by 1 plus beta into RC divided by RC plus RB. So ഇവിടെ നിങ്ങൾ ഒരു കാര്യം ശ്രദ്ധിക്കുക, stability factor is dependent on, here also it is dependent on beta അല്ലേ, but here നമുക്ക് RCയും അതുപോലെ RBയും കൺട്രോൾ ചെയ്യുന്നത് വഴി നമുക്ക് ആ സ്റ്റെബിലിറ്റി ഫാക്ടർ കുറക്കാൻ പറ്റും അല്ലേ. സോ collector to base bias circuit in the case we can say that it is more stable than fixed bias circuit, because fixed bias circuit the stability factor is equal to beta plus 1. ആയിരുന്നു. ഇവിടെ എന്താ, നമുക്ക് by adjusting collector and base resistance we can adjust the stability factor. So this collector to base bias circuit is having more stability than fixed bias circuit എന്ന് നമുക്ക് പറയാൻ പറ്റും. Okay, now coming to the voltage divider bias circuit. This is the circuit for voltage divider bias. Okay, and here stability factor is defined as S is equal to RB by RE. So here you can see where RB means base ഉള്ള equivalent resistance ആണ് ഈ RB എന്ന് പറയുന്നത്. RE is the emitter resistance. So here stability factor is dependent on RB and RE. Actually stability factor equation എങ്ങനെ വരിക എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ beta plus 1 into RB by RE all divided by beta plus 1 plus RB by RE. Sorry, ഇവിടെ 1 plus ആണ്, 1 plus RB by RE. So ഇവിടെ നമ്മൾ അപ്രോക്സിമേറ്റ് ചെയ്യുന്ന സമയത്താണ് നമുക്ക് എന്ത് കിട്ടുന്നത്, RB by RE എന്ന് കിട്ടുന്നത്. സോ ഇത്രയും നേരം നമ്മൾ സ്റ്റെബിലിറ്റി ഫാക്ടർ ആണ് കണ്ടല്ലേ. സോ ഈ സ്റ്റെബിലിറ്റി ഫാക്ടർ വെച്ചിട്ട് നിങ്ങൾക്ക് പരീക്ഷയ്ക്ക് പല ചോദ്യങ്ങൾ ചോദിക്കാം. സോ അതനുസരിച്ചിട്ട് നമ്മൾ ഇക്വേഷനിൽ അത് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് കൊടുക്കുക. ഓക്കെ, സോ ഹിയർ യു ക്യാൻ സീ stability factor S is not dependent on the current amplification factor beta. അതേ അവസരത്തിൽ collector bias സർക്യൂട്ടിലും fixed bias സർക്യൂട്ടിലും ഒക്കെ എന്താ, stability factor is dependent on beta. Here it is not dependent on beta. So here S is depending on the base equivalent resistance RB and the emitter resistance RE in the case of voltage divider bias circuit. So we can say this circuit, that is voltage divider bias circuit, is more stable. It is the most stable biasing circuit. Okay, so this is all about stability factor. So with this I am concluding today's topic.